As a quick side question, how many of you have done AC circuit analysis before? With complex numbers or phasors?
It's been a while.
Okay.
It's been a while.
Occasionally I have a student who's done it through some engineering course they've taken. There's another way of doing analysis of these. We're gonna still start in the same place. I'll eventually get to the point where I'm gonna solve it using phasors, which is the traditional physics approach. Then I'll do it with complex numbers, which is the electrical engineering approach to it. And then you decide which one you like better. All right, any questions at this point?
In construction and building and stuff, I've dealt with like single phase power and three-phase power. Is this the same form of phase?
It is the same form of phase, because the three-phase or single phase is, you basically are sending voltage or power or current, however, what do you want to, like that. In three-phase, you have one that's like this, you have one that is kind of like that, and the other one which is something like that. You're sending basically three signals at once,
Okay.
so that it's never zero at any point. That's my understanding of it.
Okay.
And that is a horrible drawing. So imagine that you drew it and then you shift over a third of that distance and then a third again. So that's what it should have been.
Okay.
Is there a question?
No.
Okay.
Interesting.
All right. A C circuit. So I have a capacitor now attached to it. Going through the same type of thing that I went through before, that the change in the voltage across the power supply, and again, we're doing AC, so the delta is generally not written, plus the voltage across the capacitor is equal to 0. Same as before, this would be epsilon sub naught cosine of omega t plus or minus Q over C is equal to 0. We can solve for Q, which is the charge on the capacitor there. And that would end up being, bring that over, times C. So I have epsilon sub naught C times the cosine of omega t. But I want current. Well, I know that the derivative of current with respect to time is going to, let's try that one again. Derivative of Q with respect to time is the current. So what's my derivative?
Epsilon sub naught C W, or omega, sorry.
Thank you.
Negative sine WT, or omega T, shit, sorry. Shoot, sorry.
I missed superproofing word flipped out.
A little bit,
Do you want me to delete it from the video?
it's okay,
Okay.
as long as they'll be okay.
You want to blame somebody for it since no one sees who you are?
No.
Okay. That word was spoken by my brother. So now if I plotted it with a marker that made marks, well, I know that the voltage across the capacitor is the same as the voltage across the AC power supply, so that basically is going to look the same. God, I always draw it badly. Here's what I need to do. There, that works. So this is going to be my voltage here, the voltage across the capacitor. My current, on the other hand, is a negative sine function. So we'll go for that usual, stunning visual effect. So negative sine function is gonna look something like that. This is my current. So if I think about phasors here, got my axes, I have my voltage starting out at 0, and then is positive, getting closer to 0, and then turns around like that, because again, these phasors go this direction. So this is my maximum voltage across the capacitor. But my current starts at 0, which means it's either pointing up or pointing down, but it immediately goes negative, and so my current phasor is pointing up. Because again, the instantaneous value is the projection onto the horizontal axis, and so right after it begins, my current is negative. So for a capacitor, the current phasor leads the voltage, not R, C, leads the voltage across the capacitor by pi over 2. Sometimes books will do it the other way, and they'll say, so parenthetically, VC lags IC by pi over 2. I's in front. Yeah, we get that. Questions here?
Will they stay at pi over 2 as they rotate?
Yep. And it's something that we will exploit.
So they're continuously the same distance apart from each other.
Same angle, yes.
Okay.
Now, this right here is my maximum current. So I, M, I'm going to IC, is equal to epsilon naught times the capacitance times the angular frequency. I want to get voltage all by itself because I basically want to get something that looks kind of like Ohm's law here. So I'm going to take my CW, or I'm not doing it. Take your C omega, bring it over to the other side, and so I have epsilon sub naught equals 1 over C omega times I sub C. Now it kind of looks like Ohm's law. Ohm's law has got voltage is equal to current times something. This something right here, this 1 over C omega, that is the reactance. It is capacitive reactance. So X sub C, capacitive reactance, is equal to 1 over omega C, or C omega if you're feeling saucy. So that's going to be true regardless of what else we're doing. And now we have the third major component, the inductor. And again, this is epsilon sub naught cosine omega t. And we'll set up the equation as we did before. I know that the voltage from the power supply plus the voltage from the inductor is equal to 0. And I have to be careful here because if I'm writing quickly, my L's and my C's look too much alike. So if you can't tell what it is, please ask. So epsilon sub naught cosine omega t minus L di dt, lowercase I, is equal to 0. Bring that over to the side, I basically have epsilon sub naught cosine omega t, which would be the the voltage from the inductor across the inductor is equal to L di dt. Let's go ahead and bring L over, so di dt. This is L epsilon sub naught over L cosine of t. What is I?
The integral, all that.
And what is the integral of all that?
Epsilon sub naught over L times omega, L times omega, sine omega t. Thanks.
So, of course, the next step is to do the phasor diagram. The voltage across the inductor is just, it's cosine. My current is a positive sign, so if I plotted my phasors here, so if that is my voltage across the inductor, my current across the inductor starts out at 0, so it's pointing up or it's pointing down, and then immediately becomes positive, which means that it's pointing down. And so this time the voltage is in the lead.
Is it little I?
Pardon?
Should it be little I?
Typically you label this would be labeled with a little I right here.
Okay.
That'd be a little V. Typically you label the phasors with the magnitude. And so I sub, let's do voltage. So V sub L leads I sub L by pi over 2. So obviously, it does make a difference if you're dealing with a capacitor or an inductor about which one is coming first, whether it's the voltage comes first or the current comes first. And then, pre-pandemic, or just before shutdown, I believe. Oh, the person who actually owns that phone had a memory trigger. Now we're using V for voltage. Engineering textbooks, at least the ones that I had exposure to, originally we're using EMF instead of V for voltage. So they use epsilon, except prior to computers, getting epsilon was kind of a nuisance. And so they just said voltage, they use capital E for voltage. So if you run across that in an engineering textbook, it's probably voltage they're talking about, not energy. But it could be energy also, or electric field strength. Can't use it too many times. So for an inductor, the voltage comes before the current. For a capacitor, the current leads the voltage. So you have Eli the Iceman as a memory trick. And that has actually stuck with me for a couple of years now, so. If you've got your own way of doing it, great. Oh, inductive reactance. So we end up, so we have epsilon sub naught over L omega sine omega t is equal to I. That's what was written there. This right here would be the maximum current, so that's I sub L. So we have epsilon sub naught over, get some contrast here. epsilon sub naught over L omega is equal to I sub L. Bringing this over so we get it into the Ohm's law form, we have this voltage, or this maximum voltage, is equal to I across the inductor times this L omega. And that is the inductive reactance. And now we've established the foundation. It's just a matter of how do you actually apply this stuff. Questions before we actually start applying? All right, let's just start out with an RC circuit. Solve it using the phasor diagram. An AC RC circuit, an RC AC circuit. Now, what is going to be common to what's common to all the components here? What's common to series?
Current,
Say it again?
current,
Yes. So current is the same for all of them, so I'm going to start out by drawing my current phasor. Now, you can start it anywhere. I tend to draw it in the first quadrant. I pretend it's 30 degrees, but usually I draw it closer to 45. So that is my current. That is the current across the capacitor. That is the current for the resistor, and that is the current for the power coming out of the power supply. Because the current's the same, that's the exact same phasor. Technically, it's three phasors on top of each other. My voltage phasor for the resistor, we go to my rule over here, they are in phase. So my voltage for the resistor is going to be right over top of it. Now I tend to draw the second one, whichever one it is, smaller. So I'm doing that here. So that's the voltage for the resistor. Now I want the voltage across the capacitor. And for the capacitor, the current leads, so my voltage lags. That's a right angle there. And this is the voltage for the capacitor. So I have voltage and current for my resistor and capacitor, and I just have current for my power supply. I need voltage for the power supply. Think back to when you're dealing with DC. What do you know about the voltage of the power supply compared to the other two voltages?
the sum of them.
So my voltage for the power supply, my phasor is just the sum of these two, and you add them like vectors. They're at a right angle to each other. And so that's the phasor diagram for this particular circuit. Let's actually do some equations here. I know that epsilon sub naught squared is equal to VR squared plus VC squared. Because I just added vectors that were right angles to each other, and that's the Pythagorean theorem. This is true for this situation. This is not a generic equation. The generic stuff is over there. I know that my voltage here, my voltage across the resistor is equal to IR. Ohm's law applies to the magnitudes or the amplitudes. So this is equal to I times R squared. For the voltage of the capacitor, I've got my Ohm's law equivalent. So that is, or analog, V equals IX, subscript C. I have I squared that I can factor out, and I'm left with R squared plus XC squared. If I take the square root of both sides, I get epsilon sub naught is equal to I times the square root of R squared plus X sub C squared. And it sure be nice if we had an Ohm's law equivalent or analog for the overall equation, and we're in luck. Epsilon sub naught is equal to the current flowing out of the power supply times the impedance. So for this circuit, the impedance for this circuit is the square root of R squared plus X sub C squared.
You said that is specific to this, right?
Yes, yes. And I do need to warn you, way too many students have made this mistake. Eventually I'll get to the end of chapter 33, here we go. So the series of equations that I give you are, there's a whole slew of equations here. This is in the summary section. And, there we go. There's an equation right here for the impedance. Z equals the square root of XL minus XC squared plus R squared. That is specific to an RLC series alternating current circuit. It is specific to one type of circuit. Please do not use this equation unless you have the resistor, inductor, and capacitor all in series with an AC power supply.
Does the order matter, or is it just the fact that they're all in there?
The order does not matter.
Because you're in series.
That's an RLC series circuit, yes. Which we'll go into, I'll explain where that equation comes from, but that equation is specifically for RL, for this. It is not the same equation, the impedance